Welcome to Foundations of SKA, Entropy-Driven Neural Learning. This course introduces the Structured Knowledge Accumulation framework from first principles, based on the paper, Structured Knowledge Accumulation, an autonomous framework for layer-wise entropy reduction in neural learning. SKA defines entropy as a dynamic, continuous measure of knowledge alignment in neural networks. The central result is that the sigmoid activation function emerges naturally from entropy minimization, not as an arbitrary design choice, but as a mathematical consequence of how knowledge organizes itself. The course unfolds in 9 modules. Before we begin, here's what you will need: linear algebra, vectors, dot products, and matrices, basic calculus, derivatives, and integrals, and familiarity with neural network concepts, neurons, layers, and activation functions. Throughout this course, we use 2 key quantities: z, the weighted sum of inputs at a neuron, what we call the knowledge, and d equals sigma of z, the sigmoid output, which we call the decision probability. If you are comfortable with these, you are ready for this course. Module 1. What if learning was never global? This module challenges the foundational assumption that learning must be global and introduces the paradigm of local entropy reduction. We examine the unquestioned axiom that has guided AI since 1986, that neurons need global feedback to learn. We look at what biology has always known about forward-only, local learning, and we introduce a different principle, each unit reducing its own uncertainty. Module 2, the hidden signal. This module reveals that the entropy signal z times dd has been present in every forward pass of every neural network, hidden in plain sight. Every forward pass computes z and d. Their product is the local entropy signal, and it is sufficient for each unit to learn autonomously. The signal was never designed. It was always there. Module 3, entropy as a path integral. Here we develop the core SKA entropy formulation, h equals minus 1 over ln2 times the integral of z dd. We define z as structured knowledge, dd as the infinitesimal change in decision probability, and show how entropy captures the accumulation of knowledge across forward steps. Module 4, the sigmoid emergence. This module proves that the sigmoid function emerges naturally from continuous entropy minimization. We substitute the key relationship between z and d into the SKA entropy, evaluate the integral step by step, and arrive at an exact result. SKA entropy equals Shannon entropy. The sigmoid is not a design choice. It is an emergent property. Module 5, the fundamental law of entropy reduction. We derive how entropy decreases as knowledge accumulates. The partial derivative of entropy with respect to z gives us the fundamental law. Entropy reduces through the alignment of knowledge with decision probability. This is a forward-only mechanism, no backward pass required. Module 6, layer-wise local learning. This module generalizes from single neurons to multi-layer networks. We introduce the coherence relation, the cosine alignment between knowledge and decision shift vectors, as a measure of learning quality. We derive the weight update rule and the governing equation for layer-wise entropy reduction. Module 7, tensor-based implementation. Here we show how SKA maps to efficient tensor operations. The knowledge tensor, the decision probability tensor, and the shift tensor allow parallel computation across layers and steps. We derive the tensor forms of entropy computation, entropy gradients, and alignment measures. Module 8, entropy evolution and experimental results. This module presents the experimental behavior of SKA. We observe entropy convergence across layers, cosine alignment evolution, output decision probability distributions, Frobenius norm growth, and U-shaped entropy trajectories. These results demonstrate self-organizing entropy minimization in practice. Module 9, code walkthrough, reproducing the results. The final module walks through the standalone SKA implementation, 428 lines of code that map directly from the mathematics. We show how to run the code on NIST, reproduce all paper figures, and verify the theory experimentally. The code is available on GitHub. Those are the 9 modules of this course. Let us begin.